Hey, good morning, everybody. This is Mr. Aynesworth, and we're going to get into Unit 7 here. And we're going to start the discussion with going over the three basic functions, sine, cosine, and tangent, and their reciprocal functions, and then get right into the tangent function and focus in on the tangent function and how it can be stretched or compressed either vertically or horizontally. So let's go over some basics first, and let's start off with the circle with radius r here. So let's draw some pictures and recall the basic definitions of sine, cosine, and tangent. So I'm going to take a look at the circle here with radius r, and if p is at x comma y, that means that the horizontal distance here is x and the vertical distance is y. So I want you guys to get your eyes on the triangle here. I'm going to talk about this little guy, where the angle here inside the triangle is theta, and from this right here we can define the following six functions. So let's do that. Let's start off with the Pythagorean relationship first. So from this triangle, we can see that x squared plus y squared is equal to r squared. We can see that. That's just straight from a right triangle trig. There's a right triangle in there. And then also in here, if we remember our famous acronym SOHCAHTOA, okay, SOHCAHTOA, we can define all three trig functions and their reciprocals pretty easily. Okay, so let's do it. Cosine of theta here. Cosine of theta is to be adjacent divided by hypotenuse, and that's going to be x divided by r. Okay, I'm going to just go basically based upon the previous stuff that you already know. And we know sine too. Sine is opposite divided by hypotenuse, and that's the ratio of y to r. Okay, so y to r. Y to r. Tangent can be defined in terms of sine and cosine first, so I'm going to do that first. So it's going to be defined as sine of theta divided by the cosine of theta. But if you look on the diagram here and you take the tangent of theta, well, that's the opposite side y divided by the adjacent side x, and so I can rewrite this as y divided by x. Okay. Knowing that, you can get the reciprocal functions. Okay, so the reciprocal of cosine is called the secant function. Now, secant is spelled like this right here, and a secant theta is a reciprocal of cosine, so I can write it as 1 divided by the cosine of theta. And then if you take the reciprocal of x divided by r, you get r divided by x. Okay, they're reciprocal. And I'll apply this here in a minute in example 1. The reciprocal of sine, well, that's cosecant, okay? So cosecant, that's how you spell it. CS is the abbreviation, and the reciprocal of sine is called the cosecant function, and the reciprocal of sine theta is 1 divided by sine theta, which if you take the reciprocal y over r, you get r over y. And then of course the reciprocal of tangent is called cotangent. Okay, so this is called the cotangent, it's cofunction. But we abbreviated just COT for cotangent. And the reciprocal of sine over cosine is cosine theta divided by sine theta. And the reciprocal of x, or y over x, is x over y. Okay, so once we get our six basic functions, now you just get to play with them and work with them a little bit. So let's go to example 1 and just kind of play the game. We've done this before for sine and cosine, and now we do it for all 6 functions. So the first thing we do is we plot 4, 3, and that's going to be right 4, down 3. So let's go right 4 units, okay, down 3 units. And you're at this point P, and we don't know the radius right here, so R, so we got to find that first. So you got to find the radius. So you apply the Pythagorean theorem again. That's why I went it over in the very beginning. Because if you have any right triangle, and this is a right triangle here, then the Pythagorean theorem applies. Okay, so 4 squared plus negative 3 squared is equal to r squared. And then we have 16 plus 9 is equal to r squared. That gives us 25 equals r squared, and obviously the radius has to be 5, so I'm going to put a 5 there. Okay, so once you find the radius, then you just write your ratios, okay? So remember, x is 4 and y is negative 3, and the radius is 5. Okay, so 3, 4, 5, special Pythagorean triple, it's called. Let me write that down in the margin. 3, 4, 5. It's called a Pythagorean triple. They come into play a lot, so you might want to memorize that one. Okay, so cosine of theta is x to r. So x divided by r, and so that's 4/5, okay? If you know cosine theta, then you know secant theta because it's reciprocal. So I'm going to write the word reciprocals here. So if you know one, you know the other one, okay? Reciprocal. So what do we have? Let's take a look. So the reciprocal of 4/5 is 5/4. Sine of theta is y divided by the radius, y to r, and this is going to be negative 3/5. Then the reciprocal of that, well, that's negative 5/3, okay? Tangent of theta is y to x, okay? And then you get negative 3/4 here, and then you reciprocate that, you get cotangent of theta, which would be negative 4/3. So if you know one, you know the other one, okay? Because they're reciprocals. That's the relationship between secant and cosine, and cosecant and sine, and cotangent and tangent. Okay. So, let's see here. Now let's talk, let's evaluate. Let's do that. Okay, so over here we want to evaluate, and we want to use the reference angles. Okay, we've done this for sine and cosine. Okay, so now what we want to do is work with the other functions as well. We're going to be using our special right triangles, so let's go off to the side and let's draw the 30, 60, and 90. So 30 up here, 60, 2, 1, rad 3. In case we have the special, the 45, 45, 90 here, and that's going to be 1, 1, root 2. Okay, and again, SOHCAHTOA. That's all you really need. You could use the unit circle here, but it's a lot easier than that, guys. Okay, so here we go. We're going to write it in terms of the reference angles. Okay, so the reference angle of 150 is 30, because if you take 180 minus 150, you get 30, okay? Now the question is this negative or positive? So this is a quadrant 2 angle, and cosine's negative in quadrant 2, so I'm going to rewrite it as negative cosine of 30 degrees. All right. And then you look at your triangle, and cosine of 30 degrees is rad 3 over 2, so you get negative rad 3 over 2. 5/3 pi is in quadrant 4. Okay, 1 2/3 pi is quadrant 4. You go 1 pi around plus 2/3 more, you're in quadrant 4. The reference angle is pi thirds. Sine's negative there, so this is negative sine of pi thirds, which is 60 degrees. And if you look at the triangle here, the sine of 60 degrees is root 3 over 2. So I get negative rad 3 over 2 here. Okay, next one. Pi force is 45 degrees. And if you take the tangent ratio, which is opposite divided by adjacent, that would be 1 divided by 1, or 1. Okay. Now comes the tricky part, the reciprocal functions. Okay, so here's how I think about it. There's different ways to do this, but here's how I think about it. 5/4 pi is quadrant 3, okay? 5/4 is 1 1/4, which is quadrant 3. Halfway around plus a fourth more pi. So now, secant is a reciprocal of cosine. So I'm going to go off to the side here, and I'm going to be thinking, okay, what's the cosine of the reference angle pi force? Okay, I know cosine's negative there, so this is a negative number here. So I need to be thinking, you know, what's the negative secant of the reference angle pi force? To get that, I think whatever cosine of pi force is, and then I reciprocate it in my mind. Looking at the triangle, I know cosine of pi force is 1, not negative. Let me change that, 1 over rad 2. But if you reciprocate that, okay, the secant of pi force is just rad 2, because you just take the reciprocal. So this has to be negative rad 2. Okay, next one, cosecant of 7 pi 6. Now cosecant is the reciprocal of sine. So now I'm thinking, okay, the reference angle for 7/6 pi is pi 6, which is 30 degrees. The sine of pi 6 is rad 3 over 2 here. Now this is quadrant 3. Sine's negative there, so this is going to be negative cosecant of your reference angle, pi 6. So to evaluate this, you want to know what sine of pi 6 is and then reciprocate it. Okay. So what's sine of pi 6? Well, sine of 30 degrees is 1/2. Oh, let me see. Why did I put root 3 over 2? Scratch that. I don't know why I put that. Sine of 30 degrees is 1/2. Sorry. I don't know why I did that. So 1/2. And then you take the reciprocal of that, you get 2. So this has to be -2. Okay, apologize for that. I was just not thinking clearly right there. Okay, I'm human too, guys. Okay, but at least I caught my mistake. All right, last one here, cotangent of 3/4 pi. Let me see, 3/4 pi is quadrant 2 now. It's a reciprocal of tangent. And the reference angle for 3/4 pi is pi fourths. So I need to know what this is. What's tangent of pi fourths? And we just answered it earlier, it's 1, right? So, but this is quadrant 2, and sine's positive, cosine's negative, so this has got to be a negative number. So this is going to be a negative cotangent of pi fourths, which is the reciprocal of tangent of pi fourths, which is 1. So this has got to be -1. Okay, there's different ways you could do that, but that's how I think about it. Notice I didn't even use the unit circle here. I just used reference angles. Okay, so that's the first part. Let's get into the first goal here on tangent here. And we want to understand how to stretch or shrink the tangent function, okay, in the form of y equals a times tangent of bx, both vertically and horizontally. So the first thing what we're going to do is we're going to take a look at vertical change. We want to analyze the 3 functions, okay, tangent x, 2 times tangent x, and 1/2 of tangent x. What happens if you multiply the function by 2, and what happens if you multiply it by 1/2? All right, what's the period of tangent? Does it have a max? Does it have a min? Or does it behave totally differently than the sine and cosine functions that we studied earlier? And then what are the answers to all these questions down here below? All right, so we have technology in this class, so what we're going to do is we're going to use it. We're going to go to Desmos here. And the goal of this one is to understand where is the tangent function defined, where is it undefined? Okay, to answer that question, we investigate using our best friend Desmos. Okay, so let's do that. Okay, dokie here. All right, so what we want to do is type all these angles in. So when you start fresh, I'll just start with a new blank graph here. You want to type your function in, and you're going to be obviously doing this on your own. So if you're watching this video, you should be doing this right now, split screen with me, and actually type all this in, because if you just, obviously just listen to me, you're not going to probably understand what's going on. Now, looking at this crazy graph, it's a little intimidating, and it really doesn't show any vertical asymptotes, and it really doesn't show you what you need to see. So we're going to dig a little deeper here. We're going to figure out where is tangent defined, okay, at all of these angles. So to do that, you go up at the top here. And by the way, click on the save button, and then save your work. Call it 7.1. We're in Unit 7, first lesson here, so call it 7.1. There we go. And save your work, okay? Click on the gear at the top, change it to a table, and what we're going to do is we're going to delete all these first because they're not appropriate, because we have totally different angles for the tangent function. And again, you just type it in. So negative pi divided by 2, and then you hit return. And then negative 5 pi, negative 5 pi divided by 12. Okay? Oop. Make sure you double check there. And then go ahead and just go all the way through, enter all the angles in. So I've already done this, so I'm just going to speed things up here. Where'd it go? There we go. Okay, so once you have all your angles in, you get to take a look at it here. Now, one of the things that you want to figure out is, like, where is this function undefined? Okay, so let me just change a few things here. Go full screen so you can take a look at this here. It's not behaving. Okay. There we go. go. I only want to look at one function at a time, and I have a lot of functions loaded in already. You may not. Okay, so one of the things that you guys need to do is figure out where is this function undefined, and it basically tells you up here in the table. So it's undefined at negative pi halves, okay, at pi halves, and 3 pi halves. Wherever it's undefined is what's called a vertical asymptote. So I want you to enter these vertical asymptotes in. So type in x equals negative pi halves, and then x equals pi halves, and then 3 pi halves. So you can see this. And when you want to change it to a dotted line, you just click on your gear here, guys. Click on the color, and then select dotted line, okay? It's that simple. And if you do not see the multiples of pi halves there on the x-axis, click on your wrench right here. And then what you do is you start on the x-axis here. You go from negative, let's say pi, to, no, probably 2 pi is good. Okay, go to 2 pi. And then step it out. The step, type in pi divided by 4, or pi fourths, that's 45 degrees. And then you'll see the x-axis change. Okay, and then you'll see multiple periods of tangent. Okay, so notice the portion that repeats right here. So we have our function here, the table on the left, we have the graph on the right. The points in the table are actually plotted for you, which is kind of nice. And notice that it repeats between, okay, these vertical lines called asymptotes. And you notice the distance from negative pi halves to pi halves. The distance there is pi radians. So this period is actually pi, not 2 pi like with sine and cosine. All right, so let's go ahead and let's bring our lesson back, and let's write down a few things. Okay, first thing, we got to bring in our numbers here. So let's record our values. So at negative pi halves, it's undefined there. Okay, we have a vertical asymptote. Okay, at x equals negative pi halves, so record that. At negative 5/12 pi, it's about negative 3.73. Just go ahead and jot down the values. Negative 1, 0, 1. Oops. Yeah. Oh, I missed 0 in there. How did I miss that? That's weird. So, 0 gives you 0. Okay. Pi fourths 1. Oh, you know what? I have duplicates. There we go. So pi fourths. Oh, my table's fine. Okay, sorry. I didn't realize that I typed in duplicate values, so I just fixed that. So pi fourths 1, 5 pi 12, so you get 3.73. Pi halves, it's undefined. There's a vertical asymptote there. So x is equal to pi halves is another vertical asymptote. VA is vertical asymptote. At 3/4, you get negative 1, and you get negative 3.73, and a pi gives you 0. Then you get 1, 3.73. Notice the values repeat, by the way. That's one of the things you can see in the table is that the values repeat. Because it's periodic, guys. Okay, so x is equal to 3 pi halves, and that's another vertical asymptote. Okay. So now what we want to do is we want to sketch the function. And I'm not going to, I'll screenshot this and put it off to the side, but I want to talk about how do you graph this by hand and how many points are required, because this is a little different than the cosine and sine function. So first of all, let me expand the graph here a little bit. Let's take a look at one period only here, okay, which is between negative pi halves and pi halves. So what you want to do is you want to sketch the vertical asymptotes. Okay, put them in red, so switch to red and do what I'm doing. This is x equals negative pi halves. We call that a vertical asymptote. It's guiding lines, basically. Okay, it helps you sketch the function. So every student in pre-calc that sketches a tangent function draws the vertical asymptotes and plots the 3 points that you see close to the origin. So tangent of 0 is 0. Tangent of pi fourths is 1. Tangent of negative pi fourths is negative 1. And then from there, you sketch, okay? And it's asymptotic. And it's got to go through these points. Oops, let me try this over again. So it curves in a very special way. Okay, so that's one period of tangent. but it says graph 2 periods. So I'm going to graph the other, there we go, the other asymptote at 3/2 pi. So switch to red. So the distance between the asymptotes is the period of the function. Okay, so between negative pi halves and pi halves, well, guess what? That's pi radians. So the period of this function is actually pi radians. Okay, it repeats every pi radians. So what you want to do is you want to plot the same 3 points. Okay, so take these 3 points and then just translate them over, and then sketch. Okay, so here we go again. Okay, so there's 2 periods of the tangent function, and you know this thing goes on and on and on. Okay, that doesn't end. That's why they call these periodic. Okay, so the period is different. It doesn't even have a max or a min, like the cosine and sine function does, because obviously this thing goes infinitely up and down, as you can see in the graphs here. Okay, so what I want to do is, well, before I screenshot, what we're going to do is we're going to talk about a few other things. So let me go back to the lesson here, and let's talk about domain and range. Actually, let's pull in the other 2 functions and actually view that too. So let me go back to Desmos actually. Okay, I don't know why it keeps doing that. Okay, so what we want to do is put the other 2 functions in. So type in these guys right here, and then I want you to colorize them. So if they're not different colors, then make them different colors. You just click on your gear, click on the color, and you could change it to any color you want. Keep all the vertical asymptotes red though, and keep your functions in some kind of dark color. Okay, so let's take a look at what we have here. So we have all 3 functions in. So I have, the one in black is my parent function tangent of x. The one in purple is 2 tangent x. So look, it's all color coded here, guys. Okay, so focus in on this right here. There we go. And then, actually, yeah, there you go, that's good. So, and then the green one, that's 1/2 tangent x. So keep that in mind. Okay, I want to screenshot here, and then you can see where the points they go through. Those are the special points that need to be plotted. So go ahead and screenshot that and bring it in right here, and then let's just copy this whole thing right here, and let's bring it in. So when you put it in your OneNote here, and just put it off to the side. Okay, so click on your text box here, press and hold on the outside of your document, and it will pop right in there. So now we know what's going on. So in our screenshot here, the black one, okay, this one here, ooh, that's too thick. Okay, so the black function is our parent function, the one in black. Okay, so y1 is equal to tangent x, and that's our parent. Okay, that's what we graphed in our OneNote. The one in purple, as you can see on the left over here, it says 2 tangent x, so this purple one. Okay, so y2 is equal to 2 times tangent x. Okay, and the green one, well, guess what? That right there is 1/2 times tangent x, because that's what it says over here on the left, the green one. Okay, so what does the coefficient here, okay, and again, so y is equal to a times tangent x here. What does the lead coefficient a do to the function? Does it stretch it out horizontally or vertically? So here, notice that in the parent function here, a is 1. Okay, in y2, a is 2. You can just see it, 2 times tangent x. And then, of course, a is 1/2 down here in the green one. So when a is 2, when a is bigger than 1, all right, notice it, the y values change. They get twice as high, okay? So pi force comma 1 is on the parent. Well, guess what? This point right here is pi force comma 2. The y value is double. Okay, so it's been stretched out vertically. Okay, so this one here has been stretched out vertically. Okay, because we double the y values. If a is 1/2, guess what? At pi force, instead of pi force comma 1, is pi force comma 1/2. Look at right there. That right there is pi force comma 1/2. The y values are half as big. Okay, so it's like a shrink, a vertical shrink. So in green, when a is less than 1 is a vertical shrink, I guess. Or vertical compression, however you want to say it, shrink or compression. Okay? So notice that the period for all of them is still pi. Okay, so the period from here to here, so the period is pi for all three of them. So A does not affect the period. It only affects, the slope of it, not how, not the period at all. In fact, it doesn't even change the concavity. So notice from pi halves comma to pi halves to 0 here, concave down. So let me annotate that from here to here, right here, from negative pi halves to 0, okay? In that interval, it's concave down. Concave down. They're opening down. But if you look on the other side, from 0 to pi halves, they're all facing upward, okay? So here, from 0 to pi halves, 0 to pi halves, concave up. That answers our other questions. Okay, so let's just take these results, let's bring them in over here. Okay, so on our main graph here, so let's see here. What's the domain of tangent x? Let me see, no, I haven't talked about that yet. Okay, so domain of the function. Okay, so tangent's defined everywhere except the asymptotes. So, so let's write that out. So here we go. So where's my pen here? So domain, which is your set of all input values. Okay, all reals except pi halves, 3 pi halves. And if you look at decimals, it keeps on going on here. So let me just bring this in. There we go. Whoa, Jesus. There we go. So notice it has asymptotes at 1/2 pi, 3/2 pi, 5/2 pi, 7/2 pi. Okay, so basically pi halves plus multiples of pi. So let me write that out. So all reals except these values here, dot, dot, dot. And the way you write that, x is not equal to pi halves plus multiples of pi, which is written as k times pi. Okay, where k is, some integer. So integer. If you don't know what that is, I'm talking about -3, -2, -1, 0, 1, 2, 3, and so on. Okay, those are integers. Okay, why do you have to add multiples of pi to pi halves to get all these values? Well, take a look at this right here. From pi halves to 3/2 pi, well, guess what? That's one period. From 3/2 pi to 5/2 pi, you add pi, okay? So this portion right here, this is called multiples of pi. Multiples of pi. That's how you write it mathematically, okay? The range is unlimited, right? It goes infinitely up to, to positive infinity, and infinitely down to negative infinity. So the range is all reals. Okay, so all reals here. Okay, you could use that fancy real number symbol. Okay, where is it concave up? Concave up from 0 to pi halves. So 0 to pi halves. And then on concave down, well, so it's down from negative pi halves to 0. So from negative pi halves to 0. And then for cosine, for 2 tangent x, well, let's go back to the graph here. So notice that for all three of these functions, whether we talk about the tangent function or 2 times tangent x or 1/2 times tangent x, it's concave up and down or concave down on the same interval and concave up on the same interval. So that does not change. The concavity doesn't change. Okay, so let's just bring our answers over here. Same intervals here. That doesn't change. Okay, and then lastly here, explain the effect of A on the function. Okay, so A stretches or shrinks in the function vertically. So A stretches, okay, or shrinks. Yeah, I guess you could say compresses, if you want to. Compresses the tangent function vertically. Vertically is the key word. Okay, it does not affect the period. It does not affect the period. There we go. So what I need you to do now is to take this idea, okay, using all your technology right here, and investigate the other case. What happens if you multiply the angle by something? So in this activity, and this is what you guys are going to do on your own, you're going to take your parent function and compare it to y equals 2x, y equals tangent of 2x. Okay, so now notice that you double the angle here, and then the third function here, y equals tangent of 1/2 x. Okay, so now we affect the angle. Okay, so now we keep a equal 1. So notice the lead coefficient is 1 in all of these, but we change b. Okay, so it says up here, keep a equal to 1 and you change b. So here, b is equal to 2, and then here, okay, b is 1/2. What kind of effect does this do? So I want you guys to do the same thing as we did here. You're going to go into Desmos here and put those functions in. Figure out where the new asymptotes are and draw them as dotted lines in red. Okay, screenshot everything and include the screenshot over here. So screenshot your results or your graphs in Desmos and import them. Import. And then, okay, so they should be here, okay? And then you're going to identify all these questions right here, or answer all these questions. What's the new domain? What's the range? Where is it concave up? Okay, does the period change? And then what's the period of the function? Right here, this is a very important thing. Is it the same or is it different? Or has the period been affected? So this is your big question right here. And you're going to do that after you put these functions in Desmos. So do a little exploration. So your homework now is not formal homework, it's a discovery, and you're going to be using a lot of Desmos. All right, and then when you get back to class, we will check your answers together. Okay, and this is just practice on the next page, which I suggest you do. Okay, this is Mr. Aynesworth here. Hopefully that gave you an idea of what happens to the tangent function and how the tangent function is created, where it's defined and undefined, and so on. And of course, we went through the basic definitions of all 6 trig functions. Okay, this is Aynesworth. I will see you in class or in my next lesson. Take care. Bye-bye.